Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Lecture 4, Orbits, Part 4. And in Part 4 today, we will cover launch windows and orbital rendezvous. You've probably heard it said that there's a certain, you probably watched a certain launch and they said we've got 5 minutes in today's launch window, or we've got an instantaneous launch window, which means they have to launch right at a certain given time. And the question is, why do launch windows occur? What's special about launch windows? And we'll just go into some of the basics about that now. And we'll also talk a little bit about the basics of orbital rendezvous and how you rendezvous two spacecraft in orbit. So the first thing to know about launch windows is that if you launch due east from a given launch site on the surface of the Earth, the inclination of your orbit is equivalent to your latitude on Earth. So let's use Cape Canaveral as an example. Cape Canaveral is located at 28 degrees north latitude. If they launch due east out of Cape Canaveral, they will end up in an orbit that is inclined 28 degrees with respect to the equator. If they want to get into an orbit that has an inclination of 0 degrees, once they're in orbit, they will have to do a plane change maneuver. Now, it may not seem obvious why this is true, but this diagram here kind of helps show what's going on. If you launch from Cape Canaveral in Florida right here, and you launch due east, of course, as you launch due east, your orbit has to orbit around the center of the Earth. And so even though you launched due east, your orbit will be inclined by about 28 degrees with respect to the equator. So you'll end up in an inclination of 28 degrees. Now, you can aim further north or further south than that, but in any case, you're going to end up with an orbit that is inclined more than 28 degrees. It turns out not only is this the inclination you get if you launch due east, but it is also the minimum inclination you can get. So there are advantages to having your launch site close to the equator. For example, the French launch site in South America is very close to the equator, and it allows them to not have to do plane changes or very small plane changes to get into geostationary transfer orbit. On the other hand, in Russia, their launch site is very far to the north, up at a latitude of about 48 degrees. And so in their case, their orbits by default are highly inclined. And if they want to reach a geostationary orbit, they have to do a very significant and very expensive plane change maneuver. So the first thing to know about your launch site is, as I said, that the latitude of your launch site determines the inclination of an orbit if you head due east. Now, you can change that by heading off in a different direction. For example, the International Space Station is inclined to the equator by about 51 degrees, and we can reach that from Cape Canaveral by launching not due east, but by launching to the northeast. And here's what one of those orbit tracks looks like. So starting from Cape Canaveral, you launch to the northeast. You actually launch, as you can see, up the east coast of the United States, but not over the east coast. You're still out over water, but you launch to the northeast. Now, one of the difficulties with this is doing polar launches from Cape Canaveral. If you wanted to get into a polar launch from Cape Canaveral, you're clearly not going to launch to the north because that is over land. And if your rocket suffers any kind of failure, it's going to come crashing down on the population. We don't want that. But you also have the problem launching out of Florida to the south, and that you have to launch over Cuba. And Cuba, both you don't want, again, your rocket crashing down on land where people live, but Cuba might view this as an aggressive act by the United States. And so typically the United States does not do polar launches out of Cape Canaveral for this reason. Typically, polar launches are done from Vandenberg Air Force Base in California. It's just north and west of Los Angeles, and from Vandenberg Air Force Base, you head south over the Pacific Ocean. And as you can see, as you head south from Vandenberg Air Force Base on a polar orbit, you're out over the ocean the whole time. So if the rocket should fail and fall to Earth, it just ends up crashing down into the ocean. Because of the Bahamas, and because of other restrictions, out of Cape Canaveral, there's typically a limited range of launch directions. So you can launch to get as high an inclination as about 57 degrees, or as low an inclination of about 38 to 39 degrees. If you launch due east, you end up with that 28, 29 degrees, which is the latitude of Cape Canaveral right there. SpaceX has recently developed a new maneuver where they can do polar orbits from Florida. If they were to launch into a straight polar orbit, the flight would take it out over southern Florida. So what they do is a dogleg maneuver. They launch down this way, and then once they've cleared the southern tip of Florida, they start heading south. It does carry them out over Cuba, but by that time, the spacecraft is high enough that that if it fails, the material won't come crashing down on Cuba. Out of Vandenberg Air Force Base, they can launch due south, and they can go into a variety of polar orbits that have orbital inclinations everywhere from 56 degrees to 104 degrees. So that's what they do when they do launches from Vandenberg. In terms of Russia, their launch site is called Baikonur, the Baikonur Cosmodrome. It's in Kazakhstan, and that's located at a latitude, of 46 degrees north. But they can't launch due east, because if they launch due east, it takes their rockets out over China. And that, again, might be viewed by China as an aggressive move of launching space vehicles over their territory. So instead, out of Baikonur Cosmodrome, they launch to the northeast, which gives them an inclination of 51.65 degrees. Now, because Russia was an integral partner of the International Space Station, and it was easiest for Russia to launch into an orbit tilted at about 51 degrees with respect to the equator, that's why the space station is in that orbit. And that is why, even though a lower inclination orbit would be easier for the United States, this was picked because that was the only choice where Russia could launch into that orbit. Now, important thing to remember always is that as your spacecraft is orbiting the Earth is rotating underneath your orbit. So if there is a particular orbit that you want your spacecraft to get into, there are 2 periods a day where your launch site is underneath that orbital plane. And if you launch at that moment of time, you won't have to do an orbit plane change maneuver. So think about this orbit right here. This is the orbit of the International Space Station. It's tilted by about 51 degrees with respect to the equator. If you watch Florida on the Earth here, you will see that there's 2 periods of the day, one here, and then one when Florida is on the opposite side over there, when Florida happens to sit exactly below this orbital plane. That is your launch window. That is the moment you want to launch. If you launch at any other time, you will end up in an orbit that is significantly different and will require a significant amount of maneuvering to get into the orbit of the space station. But if you wait until Florida is underneath that orbit, that is the perfect moment to launch. So here's another way to put this visually. This yellow line here represents the orbit of the International Space Station around the Earth. And you want to launch the moment your launch pad is below that space station. Now, typically you have a little bit of maneuvering fuel, a little bit of extra maneuvering fuel so that you don't have to launch at precisely the moment that the orbit is overhead. You might be able to launch a few minutes before or a few minutes after, right, as the Earth rotates from west to east here. So this is where Florida is a few minutes before. That's where it is when it's underneath the orbit. That's where it is a few minutes after it was underneath the orbit. So typically there'll be a launch window here. Because you have extra maneuvering fuel on board, you can launch a few minutes before or a few minutes after the ideal time and just use a little bit of extra fuel to get you to the proper orbit. So, for example, and typically you will schedule your launch for the beginning of the launch window here, not the prime time in the middle of the launch window. And that's because by scheduling your launch at the beginning of the window, it gives you the maximum amount of time to fix any problems that might occur and still have your launch occur on that day. Because after all, if you miss the launch window and you no longer have enough fuel to get into that orbit, your only choice is to stand down and wait and launch on another day. And that's very, very expensive. It's also difficult on the equipment because you have fueled everything up. You now have to unfuel everything, and then you have to bring everybody back another day to do it again. So once your rocket is fueled and ready to go, you would like to get it done in that launch window. So typically you will schedule your launch for the beginning of the window, and if your launch occurs at the beginning of the window, you'll just use a little bit of extra fuel to get it to the right orbit. If there's any kind of delay, then you still have the opportunity to launch it that day. So here's, for example, what happens with the International Space Station. Here's the orbit of the International Space Station. If you launch at the beginning of the launch window, typically the launch window for the space shuttle going up to the space station was a launch window of about 5 or 10 minutes. Sometimes it was instantaneous. Sometimes they had to launch just as the orbit of the space station was right over Cape Canaveral. And if they didn't launch at that moment in time, they didn't have another opportunity. Depending on how much mass they were bringing up to orbit, sometimes that launch window could be 5 or 10 minutes. And what that means is if they launch right at the beginning of the launch window, the plane of the International Space Station is not over Cape Canaveral. It's over here to the east, because remember, the land, because of the rotation of the Earth, is moving from west to east. So what they would do is they would launch, and they would have to do this dogleg maneuver, which just means that they would fire the thrusters to move the shuttle, to bring it over, and this is on the ascent, while the space shuttle is ascending, to bring it into the same plane as the International Space Station. So that's a little bit about launch windows and launch opportunities and the inclination of your orbit and how that depends on your latitude on Earth. Let's talk now about rendezvous. And rendezvous is where you launch a vehicle from the surface of the Earth, or in this case, this is a picture of launching from the surface of the Moon, where the lunar module would launch off the surface and then have to meet up with the command and service module in orbit around the Moon. How do you do this? How do you do orbital rendezvous? Well, now we're not going to talk about the details of it because it really gets quite complex, but I'm going to give you a general broad overview of it. And the first thing I'd like to do is another case study where we study an actual case. Now, I'm going to give you a little background on this. So in March of 1965, the former Soviet Union launched the Voskhod 2 mission, which was the first time that a human did a spacewalk in space. There was a two-person crew on board the Voskhod. They were Pavel Belyaev and Alexei Leonov. And Alexei Leonov conducted the first spacewalk in history. He was outside the spacecraft for about 12 minutes. It's interesting the way that they did it. They did not have an airlock that they could attach to the spacecraft, so they had an inflatable airlock. This was actually an inflatable airlock. They opened the hatch inside. They inflated this with air from inside the spacecraft. Leonov got inside the airlock. Belyaev closed the hatch behind him. And then once Leonov was inside this airlock, they pumped the air out of it, and then he went off into space from that airlock. And then at the end of the spacewalk, he had to come back in. So this was in March of 1965. Once again, the Soviet Union had beaten the United States to what was seen as a major achievement in space, the first spacewalk by a human being. So the United States decided to answer with the Gemini 4 mission on June the 3rd of 1965. The two astronauts were Ed White and James McDivitt, and both of them would be on Gemini 4 for about 4 days was the total length of this mission. Now, the Gemini spacecraft was a two-person capsule. As we're going to see in our next lecture when we talk about, or in our next couple lectures when we talk about the history of spaceflight, the first capsules that the United States used were the Mercury capsules, and they had room for a single astronaut. And then the Mercury led to the Gemini missions, where the capsules had space for 2 astronauts, which eventually led to Apollo, where the capsule had space for 3 astronauts, which then led to the Space Shuttle, which had room for 7 people on board. But the Gemini missions carried 2 astronauts on board. The top half of the Gemini here was the capsule itself that would return to Earth, and the bottom was a service module that contained fuel tanks for maneuvering and thrusting, contained oxygen tanks and things to help keep the crew alive for many days in orbit around the Earth. So the goal of Gemini was to demonstrate a number of things. First of all, it was going to be the first multi-day U.S. mission. That is, where the astronauts would spend multiple days in orbit. As part of Gemini 4, Ed White was also going to step outside and do a spacewalk. And that is, in fact, what Gemini 4 is most remembered for. Gemini 4 is most remembered for Ed White's spacewalk, the first U.S. astronaut to spacewalk. A number of famous and iconic images out of the space program came from Ed White. What they did was they depressurized the capsule. They depressurized the Gemini capsule, so both astronauts were in spacesuits. McDivitt stayed strapped into his seat while Ed White unstrapped out of his seat and then departed the Gemini capsule and floated around for not quite half an hour before he came back into the Gemini capsule. He had with him in his hand a little thruster, and that thruster contained tanks of nitrogen gas, and he could pull a trigger and expel the gas, which would push him in the opposite direction, right? Action and reaction, to use that to maneuver around. But within a couple minutes, he exhausted all of the gas that was in that, and then ended up pulling himself back in by just pulling on his umbilical there. So what's interesting is that Gemini 4 is remembered for Ed White's spacewalk. What it's not remembered for is the failure of the first U.S. attempted rendezvous in space. See, there was the first stage that was used to get them into orbit, and then the second stage that got them into orbit. And one of the other goals of the Gemini 4 mission was that James McDivitt, the commander of the mission, would rendezvous with the upper stage of the rocket that launched them there. So Gemini 4 attempted to rendezvous with their upper stage. Now, it really wasn't much of a rendezvous because, after all, the upper stage was in essentially the same orbit that they were in. So they just had to do a little bit of orbital maneuvering to put themselves in the exact same orbit as the upper stage. Didn't really take very much. So we would call that today station keeping as opposed to orbital rendezvous. But on the very first orbit around the Earth, before the two of them separated very far, James McDivitt was supposed to try and rendezvous and keep with, or station keep with, this upper stage. So he turns the Gemini capsule around and he thrusts towards the booster. And the first thing that happens is he saw that the booster, as he thrusted towards it, ended up going away from him and ended up going downward. Now, this was a bit concerning because he was moving what he thought towards the booster and it had moved out of sight. So he ended up having to pitch the Gemini capsule nose down to see if he could see the booster, and he saw the booster down below him, so he thrust towards it. But once again, every time he would thrust towards the booster would react and it would move in a strange direction. Every time he maneuvered, it always moved off in some weird way. Now, he chalked it up to the fact that the booster was still venting some propellant that was left on board. The booster hadn't used all of its fuel and oxidizer, so it was venting some of that fuel and oxidizer, and that certainly probably accounted for some of its maneuvering. Another problem that they had was that they had no good way to judge the distance to the booster. White and McDivitt both looked at the booster, and they would estimate with their eyes how far away it was, and at one point, McDivitt estimated that the booster was 60 meters away, and White said it was 250 to 300 meters away. So the two of them disagreed by a lot on how far away the booster was. In addition, the booster had some lights on it, and they were alternately hard to see during the daylight, and then at nighttime, the lights were blinding, and the astronauts had a hard time seeing with it. Eventually, McDivitt ends up expending about half of all the maneuvering fuel that they had with them. Remember, this is all on the first orbit here, where he's thrusting the Gemini capsule around, trying to catch up with the booster, but every time he goes for the booster goes off in some weird way. He eventually uses up about half the maneuvering fuel, and McDivitt has to call it a day. He has to say it's just not going to happen on this mission because they needed that maneuvering fuel for other goals that they had to carry out on their 4-day mission. And so what has been forgotten by history is this failed first attempt at rendezvous, because the spacewalk was such an overwhelming success that everybody remembers Ed White and his spacewalk, and almost nobody remembers this aborted attempt at rendezvousing. Later on, an engineer with the Gemini Project office by the name of Andre Meyer said, "There's a good explanation for what went wrong with the rendezvous. The crew, like everyone else, just didn't understand or reason out the orbital mechanics involved. As a result, we got a whole lot smarter and really perfected orbital rendezvous maneuvers, which Apollo now uses." The problem wasn't that the spacecraft, that the upper stage was venting fuel and was moving in odd ways. It was that McDivitt and the engineers and the mission planners who went into this didn't really think about orbital mechanics. They just assumed that if you see the booster over there, that you thrust towards the booster and you'll end up over there. And the problem is every time you fire your thrusters, you're changing your orbit. And you might remember from the last lecture that when you change your orbit, weird things can happen, right? If orbital drag slows you down, you fall to a lower orbit, but you speed up. This was what was stymieing McDivitt's attempt to rendezvous. They did eventually perfect orbital rendezvous during the Gemini missions. They one of the things that they had to do to perfect this was develop a trainer. This particular trainer, there's a mock-up of the Gemini capsule here, and the astronauts would sit inside this mock-up of the Gemini capsule, and here was the vehicle that they were going to dock with, and they could practice their maneuvering, their orbital maneuvering on this in a life-size capsule with a life-size booster, with it being mounted on this gimbal so that it could tilt up and down, it could pitch up and down, it could roll side to side, it could yaw back and forth, it could translate up and down and side to side, and more importantly, eventually this simulator included all of the correct orbital mechanics in it. So to think about the orbital mechanics, let me ask you this question. A football player, he's in orbit around the Earth. So we've got, for some bizarre reason, 2 football players in orbit around the Earth. And one football player has a football, and that football player throws a forward pass, throws the football forward. What will the ball do? Go out to the lecture exercise and pick the best answer to this. What will that ball do? Will it go upward? Will it go downward? Will it go straight? Go ahead and pick what you think is the best answer to this one. So what did you think on this one? Well, this is the classic problem that faced the crew of Gemini 4, that when you throw a football forward, for example, if the Earth is down here and their orbital motion is this way, so they're orbiting this way, as you throw that football forward, you're giving it more speed. So what happens in an orbit when you fire your thruster and you give it more speed? Well, you move it into a higher orbit. Remember our Hohmann transfer orbit last time? When you're in a low circular orbit and you add speed to it, you end up boosting yourself into a higher elliptical orbit. So what they end up doing is by throwing the football forward, it moves to a higher orbit. But the thing about that higher orbit is, remember, in a higher orbit, the circular orbit velocity is slower. And so if you throw a football forward, what the football does is it actually moves upward and arcs backwards. Completely counterintuitive. But that is orbital mechanics. And you have to take that into account when you're doing orbital rendezvous. So if you give a satellite, if you give that football extra forward velocity, it will move into an elliptical orbit that has a larger semi-major axis, which means it'll move upward and away from the Earth. But that higher orbit also has slower orbital velocity and a longer period, so after you throw it forward, it will quickly lag behind you and fall behind you, and the football will never reach the receiver. So if you were in orbit and wanted to throw a football to the receiver, how would you do it? Here's the counterintuitive thing that you would do. What you would do is you would throw the football backwards, away from the receiver. By throwing the football backwards, and what you're really doing is throwing it against your orbital motion. By throwing it against your orbital motion, it will slow down. That means that it will move into a lower orbit, but that lower orbit that it moves into has a faster circular orbit speed and a shorter period, so the football will pull ahead of you, and then as it pulls ahead of you, it's in that elliptical orbit now, right? Because you gave it one push here, it's going to be in an elliptical orbit, but one orbit later, it'll meet up back up with you again, and so one orbit later, it will pass below you, come out in front of you, and then it will come up and the receiver can catch it that way. So the way you would throw a football from a passer to a receiver is you would throw it away from the receiver, let the ball go into a lower, faster orbit. When it's in that lower, faster orbit, it will pull ahead of you, but it will also pull up then and come into the hands of the receiver. When astronauts train today for doing orbital rendezvous, for example, here's a picture of the space shuttle Endeavour docked to the International Space Station in May of 2011. When we train astronauts today on orbital rendezvous, they have to keep all of these orbital mechanics in their head. They have to realize that if they make a maneuver, it's not just thrusting towards the thing you want to get to. You have to think about the consequences of that. If I move forward, that might also move me up in an orbit. It might give my orbit more energy, which would cause me to lag behind. Or if I thrust away from it, I can go into a lower orbit and catch up to it. Typically today, when we do orbital rendezvous, we designate one vehicle as the active chasing vehicle and the other one as the static vehicle, the target spacecraft that's not going to do any maneuvering. And for the space station, it's pretty obvious which is which. The space shuttle or the Dragon capsule or the Boeing Spaceliner capsule will be the active chaser spacecraft, and the International Space Station itself is just the target. We're not going to maneuver the space station around. Now, when it comes time to launch, there are two launch constraints based on orbital rendezvous. The first one we've already seen, it's the orbital plane. You need to wait until the orbital plane of the target passes over the launch site of the chase vehicle, because otherwise the chase vehicle ends up in an orbit that's inclined with respect to the target, and it requires a lot of fuel to change that orbit. So you have to wait until the orbital plane comes above the launch site. And typically that provides two launch opportunities every day, one ascending and one descending. That is, there's one where you're on where the space station is ascending over Florida, and then later on where the space station is descending over Florida. Typically we don't launch on the descending node out of Florida, just on the ascending node. But nevertheless, you might have up to two opportunities a day to launch. Then there is not only the planar consideration, getting into the same orbital plane, but there's a phasing consideration. That is, you need to launch when your target and chaser are in the correct positions so that the chaser can catch up to the target, right? So what you want to do is pick a launch moment in time where there's some angle between the target and the chaser, so that in this changing orbit, as it climbs higher and higher, it will catch up to the target. And the problem with this phasing pane is there's lots of conditions on when you can launch as well. So you know it has to occur when the orbital planes line up, but it's also constrained by things like crew schedules on both the target and the chaser. So you don't want the astronauts on the International Space Station having to get up in the middle of the night to do an orbital rendezvous. Depends on the location of the sun. You would rather do your docking during daylight hours when you can see better. Space adaptation syndrome. As I've mentioned earlier, some astronauts have a hard time adjusting to the weightless environment. For the first few hours, you can feel nauseous. You can be throwing up. Not a good time to be doing really complicated orbital maneuvers. And then things like communications coverage and everything. So determining when you can do an orbital rendezvous is actually a really complicated thing. The second thing about orbital rendezvous is it's not usually conducted using a single Hohmann transfer. Imagine that we launched the space shuttle and it's in a low orbit and we want it to dock with the International Space Station. We're typically not going to use a single Hohmann transfer to do that, because as the space shuttle then, or let me use the Dragon capsule since that's what we're flying today, because the Dragon capsule would be moving very quickly as it approached the space station, and that would be dangerous. It turns out a better way to do it, a safer way to do it, is to put your chaser vehicle into a series of intermediate orbits that are gradually getting closer and closer to the space station, gradually trying to better match the orbit of the space station. So this is typically what it might look like. The Dragon capsule would launch off the Earth and it would go into an initial elliptical orbit. So this is the orbit of the International Space Station right here. By the way, these are all, of course, grossly exaggerated, right? If this is the size of the Earth, the International Space Station is barely orbiting above the surface of the Earth. But to make it a little bit more clear what's going on, they've stretched things out a lot. So just keep in mind the space station is not in an orbit that is that high. But you have main engine cutoff, so you have your spacecraft in orbit, and the Dragon capsule will initially be in an elliptical orbit like this. And then typically they won't rendezvous right away on the same day. They might spend a day or two in orbit, and they'll spend that day or two in orbit for a couple of reasons. First of all, on launch day, the astronauts had to get up really, really early in the morning. They had to get ready for launch. They had launch. Once the spacecraft is in orbit, they've had a pretty stressful, pretty long day as it is. They're probably ready for a rest. The second thing is once they get into orbit, they might be suffering from space adaptation sickness. They might be nauseous. They might be vomiting. They probably need some time to get over that. So it's best to leave them in this orbit for a day or so before starting to do a whole bunch of maneuvering to raise their orbit to better match the International Space Station. So in between, there will be a number of phasing orbits, and these phasing orbits take their original low Earth orbit and bring it closer and closer and closer to the orbit of the International Space Station. And these phasing orbits, as you can see, they will fire their thruster here to change their orbit. So they're in this initial elliptical orbit. They will fire the engine here to boost them to a slightly higher orbit, and then boost them again to another orbit and a higher orbit. And then eventually they will boost themselves up to an orbit that matches the International Space Station. And then finally they'll get close to docking here at this point. Now, the diagram that we use to do this is what's seen from sort of an outside observer that's looking at the spacecraft from the outside. As seen from view of the International Space Station, it looks something like this. The two directions here are R bar, which is the direction towards the center of the Earth. So this is the vertical height of the International Space Station. It's in its constant orbit up here, so it has a constant height. And then the V bar, which is the direction of motion that the space station is moving. And this down here is the chaser spacecraft. And this happens to be a rendezvous that was done with the space shuttle. And so the initial ohms 2 burn right here, that initial ohms 2 burn right there, starts getting it into these chaser orbits right there. And so it gets into these chaser orbits. And what's going on here is you'll notice that the chaser vehicle is getting close to the space station and then far away, and close to the space station, which is way up here, by the way. So it's not really close, but it's getting closer to, and farther and closer and farther. What we're seeing here is the elliptical orbit. It's far from the orbit of the International Space Station. It's close to the orbit of the International Space Station. So that what we're seeing here is as it's orbiting the Earth in that elliptical orbit, it gets close to the orbit of the space station, far away, close, far away, and then it does some thruster firings. And these thruster firings are meant to first of all bring up this perigee down here and make it higher and higher. And eventually, after they get a couple of these phasing burns done, these burns, by the way, are not just bringing the two orbits closer together, but they're also lining up the Dragon capsule and the International Space Station so that when they do their final rendezvous maneuver, both of them will be in the same place at the same time. Remember, when the Dragon capsule is in this lower orbit, it is orbiting the Earth faster than the space station is. And down there, then, they can loop ahead of the space station. They can get ahead of the space station and line up so that at just the right moment, they can do the NH firing right here, the thruster firing, that will bring them up to the rendezvous with the space station. And then finally, as they do this thruster firing, they will bring themselves up to an orbit that touches the orbit of the space station. Now, the space station's not there yet. They're behind the space station, but it'll bring them up to a point behind the space station, but they're still on an elliptical orbit. So they will be brought down below the orbit of the space station, back up to the orbit of the space station, and then they will do a number of other firings until they come and dock with the space station. In fact, what the docking looks like from the outside is it looks like the chaser spacecraft is coming up and matching the orbit with the International Space Station. What it looks like from the space station is that the chaser spacecraft is coming up from below in a faster orbit, actually comes out in front of the space station and then comes back and docks with the space station like that. Now, these orbital rendezvous can take years of training to master because they're incredibly technically complex. There are all kinds of constraints that go on. So, for example, in a docking with the International Space Station right here, as they come up to that last approach up to the space station orbit, this will be during the daytime, but the sun will set here. This will be during the night portion of the orbit. Then the sun will rise, and then they will do the final docking here. The MC3 and the MC4 maneuvers is as the space shuttle, in this case, approaches the International Space Station from below, because in this case they're coming up from below to dock with the space station. As it's coming up from below to dock with the space station, they will stop at various points and do station keeping maneuvers to make sure that everything is under control and everything is working well. After all, they don't want to be closing in and closing on the space station if one of their thrusters isn't working, or they're out of alignment, or they're moving too fast or moving too slow. they need to get everything right. So there will be typically a couple station keeping where they'll stop, say in this particular case, they stopped 170 feet away from the space station. They stopped 30 feet away from the space station to let everything settle down, make sure everything was lined up properly, and then they'll make contact. The whole time, you'll notice the thrusters firing here. They can't fire the thrusters in the direction of the space station because the exhaust from these thrusters, as it impacts the giant solar arrays and other things on the space station, could damage them. So all the thrusting has to be done away from the space station. Now, there is a reason that you might want to not spend a couple days in orbit around the Earth before docking with the space station. And one of those reasons is if you're launched in a Soyuz capsule. Because the problem with the Soyuz capsule, the Russian Soyuz spacecraft, is there's very little room inside the capsule itself. This is a picture of 3 cosmonauts that are inside the Soyuz capsule. And the thing about the Soyuz capsule is there's so little room to maneuver and move around in there, is that if you get launched to space, it's really difficult to spend 2 or 3 days in orbit in such a cramped space. Now, typically the astronauts have done this, and they've done this for many, many years, and they've just put up with a couple days in a very cramped space. But the Russians have recently perfected an automated docking maneuver where they can go from the surface of the Earth. So they can launch and they can put themselves, and within a few hours, they can come up and dock with the International Space Station. So they'll do a couple orbits around the Earth. While they're doing those orbits, they're doing their phasing burns, they're getting into the right position so that they can come up and dock with the space station just a few hours after launch. That requires, amongst other things, an automatic docking in case your astronauts are feeling the effects of space adaptation sickness. And as I mentioned, they're already tired after a long day. But the Russian Soyuz capsule does have the ability to do an automatic docking. In the future, the SpaceX Dragon capsule will probably do something similar. Here on the first few test flights, they did what the space shuttle used to do, which is go into orbit and spend a couple days in orbit, testing everything out, doing those phasing burns, getting lined up with the space station, getting ready for the rendezvous. That's what they have done with the SpaceX Dragon so far. But in the future, they do have plans for doing a quick ascent where they launch up to and dock to the space station. If you haven't had the opportunity to try it, SpaceX has a fantastic SpaceX docking and simulation game where you can actually try and dock with the Dragon spacecraft to the International Space Station. It's really a lot of fun. I highly recommend that you go out there and give it a try. It gives you a really good feeling for what spaceflight is like, but you can not only move your spacecraft up and down and side to side, but you can rotate it in different ways, and then you have to fire your thrusters towards the spacecraft. It's really, as I said, it's a lot of fun. Unfortunately, it's taking a lot of time to load right now. But it's a great game and you should give it a try. So if you're curious, this is what the SpaceX docking simulator looks like. So if you click begin right here, comes up with 2 sets of controls you'll see in a second. So there's the International Space Station. You're in the Dragon capsule approaching the space station, but you're off target. So you have over here the ability to move yourself sideways and up and down, forward and backward, and then you also have the ability to roll, pitch, and yaw the spacecraft. And so you've got here, you want to zero out the roll, the pitch, and the yaw, at the same time translating yourself over and forward to get to the space station, at the same time not doing it too quickly, because if you come in too fast, you'll crash with too much energy and you'll lose. So it's a lot of fun. So in this case, for example, we can try and take out some of this roll that the spacecraft has, take out some of the pitch that we have, take out a little bit of the yaw. At the same time, I'm going to fire my thruster to start moving forward towards the space station, speed up a little bit. One thing about spacecraft is if you fire a thruster to go this way, you'll keep going that way until you fire the opposite thruster to stop. So you'll notice that if you start moving in one direction, you won't stop moving in that direction until you fire the opposite thruster. And I'll let you finish the game on your own. So if you go to iss-sim-spacex.com, it's a lot of fun. You'll spend hours trying to dock yourself to the International Space Station. It'll teach you a little bit about how you maneuver a spacecraft. Because you're already so close to the space station to begin with, there's not too much orbital mechanics that you can learn out of this. But it is a lot of fun just to play. So have fun. Good luck docking with the space station. All right. There are other times when you put a spacecraft in space and you would like it to sit still is probably not the right word, but stay in place or at least stay with you. So, for example, there are space telescopes that we want to launch off the Earth, but if we launch them to an orbit closer to the sun than we are or farther from the sun than we are, if we launch them in an orbit closer to the sun than we are, they will pull ahead of us and quickly get out of range to communicate with them. Or if we launch them further away from Earth, they will fall behind us. There are, for example, a whole series of satellites that we've launched that we would like to use to study the sun, and we don't want them in low Earth orbit so that they can see the sun continuously without passing into the shadow of the Earth. So how can we do that? How can we put a spacecraft out in space and keep it still? There are a couple special places called Lagrange points where gravity, the centripetal force, and the Coriolis force all balance one another, and you can put a spacecraft there and it will maintain that position. Coming up later this year, we will be launching the James Webb Space Telescope, and we will be launching it to one of the Lagrange points around the Earth, the L2 point. And the whole goal for launching it to this Lagrange point is we want this telescope away from the bright Earth. We want it to be in the darkness of space. But at the same time, if we were to launch it out into the outer solar system, it would very quickly fall behind the Earth's orbit and it would be difficult to communicate with it. We would like to find a point where we could put it where, as the Earth orbits the sun, it would keep up with the Earth but still be far away from the Earth. As I mentioned, those Lagrange points, those points are called the Lagrange points, and there are 5 of them. And the thing to keep in mind is the Lagrange points are not just the balancing force of gravity. So, for example, there is a Lagrange point. If this is the sun down here at the center, and this blue sphere represents the Earth orbiting the sun, there is a Lagrange point between the Earth and the sun. That's called the first Lagrange point. Now, you might think that at that point, the gravity from the Earth and the gravity from the sun balance one another. What's really going on here is more complicated, though. It's not just gravity balances, but also the centripetal force and the Coriolis force. But the thing is, if you put a spacecraft at point 1, what that means is that all these forces are balanced out, and as the Earth orbits the sun, the spacecraft will keep up with the Earth. It will sit at that Lagrange point and keep up with the Earth as it orbits the sun. So that is, in fact, the first Lagrange point. 1 there is where we have a lot of solar monitoring spacecraft. We've launched over the decades many spacecraft to monitor the sun, and we've put them at the Lagrange point 1, the first Lagrange point there, so that they're far away from the Earth, but they get a continuous, and because they're far away from the Earth, they get a continuous 24-hour-a-day, 365-day-a-year view of the sun. They can monitor the sun continuously, but at the same time keep up with the Earth and not get ahead of us or lag behind us. The James Webb Space Telescope is going to be launched out to the L2 Lagrange point. The L2 Lagrange point is about 1 million miles further away from the sun than we are or so. And that's where the James Webb Space Telescope is going to be parked. On the opposite side of the Earth from the sun is the L3 Lagrange point. That one's not very useful to us because it's on the exact opposite side of the sun from us. And then there are the L4 and the L5 points. You can use all of these Lagrange points to stay put. If you put a spacecraft at the L2 point or the L1 point or the L4 or the L5 point, it will stay there. Now, some of them are local minima, which means that if you put a spacecraft there, it wants to come back towards the center of it. And 2 of them, like the L1 and the L2, are local maxima, which means when you put a spacecraft there, it's like being on a hill between, if we have the Earth and the Moon, for example, it's like being on a hill in between where if you get a little bit too close to this one, you'll fall down towards the Earth. If you get a bit too close to that one, you'll fall down there. So it does take a little bit of maneuvering fuel to stay at the L1 and the L2 points, but for the most part, these hills are broad and flat, and it doesn't take much to stay there. But L4 and L5 are really interesting because they are minima. That is, if you think of them, they are a dip in the hill, and that means that things will tend to flow downhill and get caught there. Now, we don't really have any use for the L4 and the L5 points. We haven't really put any satellites at either of those right now. But a really good example of the L4 and the L5 points are Jupiter. Jupiter is the most massive planet in the solar system. It outweighs the Earth by a factor of 318. In fact, it outweighs all the other planets in the solar system put together. And between Mars and Jupiter is the asteroid belt. And these asteroids are on elliptical orbits, and every now and then some of these asteroids would get caught at the Lagrange points of Jupiter. So Jupiter has in front of it and behind it a series of asteroids that are caught in these Lagrange points. And they're given the names of the ancient Greek warriors. So, for example, one of them are the Trojans, the Trojan asteroids. And these asteroids are basically in the same orbit around the sun as Jupiter is, but they're circulating around these Lagrange points. In fact, if we watch the asteroids themselves, they're not sitting still at the Lagrange point. They're making a tiny little circle around the Lagrange point as the Lagrange point orbits around the sun. And what I think is really fascinating about him is one way is to think of it as like epicycles. Remember Ptolemy with his circles on circles. In fact, that is exactly what these asteroids are doing as these asteroids circle around these Lagrange points. So that is a little bit about the Lagrange points. The last thing I'll mention about orbits is using gravity assist maneuvers. Sometimes when we're sending a spacecraft to the outer solar system, we want it to get there more quickly. And what we can do is use the gravity of Jupiter especially to speed it up. Because Jupiter has a very massive gravity, and you can take advantage of orbital dynamics and allow the spacecraft to fall into Jupiter, but also allow the orbital motion of Jupiter to pull it away from the spacecraft so that in the end, the spacecraft ends up gaining velocity from its encounter with Jupiter. And that means that Jupiter lost a little bit of its velocity, but since Jupiter is so massive and the spacecraft is so small, it's inconsequential. Some of the more famous examples of gravity assists are the Voyager 2 spacecraft. The Voyager 2 spacecraft encountered Jupiter. It then used that gravity assist to send it on to Saturn, where it also gained more speed to go to Uranus and then on to Neptune right there. And you'll notice that each of these encounters, as it encountered Jupiter, it gained a lot of speed. And then as it encountered Saturn, it gained a lot of speed again, and then Uranus and Neptune. So each one of these provided a boost, and we call these gravity assists, where we use the gravity to send the spacecraft going faster. Other examples of this are the Cassini mission out to Saturn. So Cassini was launched from Earth, and then it had a gravity assist around Venus. It was actually launched on an elliptical orbit so that it would go closer to the Earth than the sun would, have a gravity assist from Venus, which would send it out by an Earth flyby out past Jupiter, and then once out past Jupiter to Saturn. And it would use the gravity of Jupiter to not only redirect it to Saturn, but to give it a boost in speed so that it could cover this distance more quickly. These gravity assists can be really quite complicated. For example, the Messenger mission to Mercury. When we wanted to launch a satellite from Earth to get to Mercury, it turns out we didn't have a rocket that had enough delta V that it could get the spacecraft directly in an orbit, a home and transfer orbit that would get us directly to Mercury. Instead, what we had to do was use a number of flybys of the Earth, 2 flybys of Venus, and 3 flybys of Mercury to lose enough speed. In this case, we weren't trying to speed the spacecraft up. To fall into the inner solar system, you have to lose speed. So at each of these encounters, we were using the gravity of the planets to slow down the spacecraft so that it could fall further into the solar system and eventually get caught in orbit around Mercury. And other missions have had incredibly complicated maneuvers using gravity assists. Back in 1985, 1986, when Halley's Comet was coming to the inner solar system, the United States decided to repurpose the ISEE-3 mission to go visit Halley's Comet. But in order to do that, they had to do a number of gravity assists and flybys of the Earth and the Moon. And then When we talk about systems like Jupiter with all of its moons and Saturn with all of its moons, we can use gravity assists of the moons to change the orbits of our orbiters. So as the Galileo spacecraft was in orbit around Jupiter, it was using the gravity of the moons, all these gravity assists, to change its orbit so that the next orbit it would swing by another moon, or I should say maybe not the next orbit, but on a future orbit it would swing by another moon. And over its years in orbit, the Cassini mission did dozens of these gravity assist maneuvers to change its orbit so that Cassini could visit other moons in the system. So that is it for Lecture 4 on orbits. We've covered pretty much everything there is to need to know about orbits. So starting with our next lecture, Lecture 5, we're going to talk about the early history of spaceflight. We'll talk about the conceptual ideas before we could even fly rockets, and then we will talk about the early rocket development and early spaceflight. So join me in Lecture 5 for the early history of spaceflight.